Hey, here we are. We're doing a exponential decay question, and we're kind of taking a swing at this from the point of view of it being a differential equation here. So we know that for exponential decay, that the rate of change of the amount, A stands for amount, is equal to some proportionality factor of the amount. Okay, so it depends on how much you have. Base is how much it changes by. Okay. And so, this is usually the case when each member of the population has a certain percentage chance of either, growing or decaying or things like that. Anyway, so this is the differential equation. We're going to use the differential equation to build this is called the general solution to the differential equation. And then we'll use the specific conditions in our question here to build, in this green part, the specific or the particular solution. Sorry, this is called the particular solution. So this is the differential equation, general solution, and particular solution. And then we're actually just solve the question way down here, okay? So starting with the idea that this is a differential equation, we do some algebra, integrate both sides, and get our integral here. 1 over a is natural log of a, integral of that. Integral of k dt is kt, okay? And we add c because we just integrated. Now to solve for c, I roll with the idea that when t equals 0, my amount is my original amount, and AO will stand for original amount. And now, basically, I take this equation, plug all that stuff in, t equals 0, A equals original amount, I solve for c. Take that C and plug it over here again, because I'm going to take this equation and use it again. And now a little bit of algebra is going to give me my general solution, okay? Subtract that over. This right here is the difference rule for logarithms, which brings me from this line to this line. And then a little bit of algebra here, oh no, this is the definition of logarithms, moving from this line to this line. And then here's a little bit of algebra, just pass that AO over, multiply it over. Now I'm going to take my general solution and I'm going to try and build a particular solution because I now have a specific condition here. And that is when half of the time has gone by, when this amount of years has gone by, half of my original amount remains. So A equals half of AO when this amount of time has elapsed. So I take that amount of time, put it in there, and I take A and change it to half of AO, and now some algebra will solve me for K. Doing this algebra, cancel the AOs, move from here to here is definition of logarithms. From here to here, just dividing by 5,730. And from here to here is the power rule for logs because it's traditional to write a 1/2, natural log of 1/2 as a negative log of 2. All right, now that I know my k, I've now discovered my particular solution, okay, which is this. And now, taking this into consideration, we want to now find the time for when 20% is left. All right, so therefore, I'm going to set these conditions up. My amount is 20% of the original amount when t equals what? And I'm solving for t. So I take all this information, plug it into here. So 20% of AO is going to be my amount. Okay. Now, again, my AOs cancel, and I'll roll through and I'll be able to solve for this t value. So rolling through this algebra here, my AOs cancel. This is the definition again, definition of logarithms. This is divide this thing over, and this is plug this stuff into the calculator and get your solution there. Okay. So there it is, a bit of a look at a exponential decay from the point of view of a differential equation. Most students start with the general solution. You kind of have this memorized, and then you use these two things to find your k value. You can actually, in a way, always memorize. If you can look for a pattern, you can get your k value memorized as well. Negative is decay, half the 2 is here, and the time always goes here. You'll see a pattern if you do more of these. And then you use your particular solution to solve for various t values and things like that. Okay. All right. There we have it.